So a pretty common situation is a current divider with two branches. And so there's a shortcut that we can use in this case. So the equivalent resistance of two resistors in parallel, the shortcut is the product divided by the sum. So that's R1, R2 divided by R1 plus R2 for this particular circuit here. And so we can write the current in one of our branches. Let's look at, say, I1 as the first branch. And we know that this will be the input current scaled by the total or the equivalent resistance. So R equivalent divided by R branch, which in this case is just R1. But we calculated R equivalent just above, so that means we have, substituting in to here, we will get R1, R2 on R1 plus R2. And this is kind of nice because we can actually simplify this equation a little bit, cancelling out those R1s there. And what we will end up with is the input current times the resistance in the other branch divided by the sum of the resistances. So key point to recognize here, we're talking about I1, but it's resistance 2 that appears. So it's the resistance in the other branch. So that's an important fact to recognize. Now, we can kind of write a general expression for that, which maybe is easier to memorize if you want to remember this rule. So the current in the branch is the input current multiplied by the other resistance. All of that is divided by the sum of the resistances. So that's the other resistance plus the resistance in the branch. So this is a little shortcut for our current divider for the common case that we have just two resistors that the current, or two branches that the current is being divided over. So I want to work through an example where we use current division to analyze a more complicated circuit. And so you might not immediately see how to use current division here, but the trick is to simplify the resistors, to combine the resistors together. So in particular, what I can do is understand or recognize I have this 20 amps that will flow into this node, and then it's going to branch off in two directions. So I'll have a current, let's call it I1, and another current here, let's call it I2. And this is a current divider. And so what I can do is calculate, well, what is the equivalent resistance of this entire side of the circuit? And that will be the resistance that I need in order to use my current divider formula. So let's actually have a look at analyzing that. So the equivalent resistance of this right-hand side, so R equivalent on this right-hand side, is 115 in series with, so 115 plus, it's in series with 50 ohms, which is in parallel with 5 plus 70. So I can kind of write down this expression for what will be the total resistance of this complete network, or this part of my network. So that's 115 plus 50 in parallel with 75. And now for the case of two resistors in parallel, we have a nice simple formula for that one. So it is the product divided by the sum. So that's 50 times 75 divided by 50 plus 75. And so I get out my calculator and I analyze this these values. So just bear with me, I will type them in and calculate. So it's 115 plus 50 times 75 divided by 50 plus 75 is 145 ohms. So I can kind of redraw my equivalent circuit that are based on this simplified set of resistors. So I have my 20 milliamp current source, which drives a 200 ohm resistor that is in parallel with this other network, which is R equivalent, which I just calculated to be 145. So now I have a simple current divider, right? So the current I2, which is this one here, that I'm trying to solve for, can now be pretty simply calculated. So I have here I2 will be the input current, which is 20 milliamps, so that's 0.02 amps, multiplied by the current in the, the resistance in the other branch. Resistance in the other branch is 200, divided by the sum of the resistances. So that's 200 plus 145. So again, I'll pull out my calculator and I'll just quickly evaluate this. So 0.02 times 200 divided by 200 plus 145 is 11.59 milliamps. So 11.59 milliamps is the current I2. So now, having evaluated this, I can go back to my original circuit and look at just this branch in isolation. So let me kind of redraw the circuit that I was studying. So I had the branch that I've just been looking at consists of a 115 ohm resistor, which then splits off, it was 50 ohms, and we had 5 and 70, so 5 and 70 ohms on this side, and then it was connected back. And I have just calculated that the current entering here is 11.59 milliamps. So again, I have a current divider circuit. And the current that I'm trying to find was this I0 was the current through the 50 ohm resistor. So looking back at our circuit, it was the current through the 50 ohm resistor. So that's actually the answer that I'm seeking in order to analyze this circuit. So again, I have a current divider. So at this node, the 11.59 milliamps that comes in is actually split off down these two separate branches. So I can kind of write down directly what will be an expression for I0. So it will be the current coming in, right, which is 11.59 milliamps. So that's 0.1159 in amps. So the current coming in multiplied by the current in the other, the resistance in the other branch. So resistance in the other branch is 75, and all of that is divided by the sum of the resistances. So that's 50 plus 75. So again, we'll just calculate all of that. So bear with me. 0.01159 times 75 divided by 50 plus 75 is 6.95 milliamps. So 6.95 milliamps will go down this particular branch. And that's kind of plausible, 11 and a half coming in, and we end up with nearly 7 going down this particular branch. So it has the smaller resistance, so I would expect it to have kind of the larger share of the total current. So that seems like a kind of a reasonable number, useful to do these sort of sanity checks in your head. Now, one point to keep in mind, this 115 ohm resistor here actually played no part in this calculation of this current divider. And basically the reason is I've already used that fact in calculating the equivalent resistance, right? It did factor into the equivalent resistance, which dictated how large the current I2 was. But here, when I have this situation, I have a particular current coming in, and the resistor can't change the size of that current. So there's 11.59 milliamps entering. It actually doesn't matter anymore what is that resistance. I just have this current entering, and then the point where I need to start doing some calculation is where the current gets divided over these two separate branches. So at that point, I use my current divider formula to evaluate it. So that's an example of analyzing a more sophisticated circuit. Basically, the one weird trick that you need to know is this idea that you can use the current divider formula multiple times. So incoming current gets split up into two different branches, and then of that branch, again, it gets split up down two different branches. And so with that, you can analyze more sophisticated circuit layouts.